Hi and welcome to this video lecture on the fundamentals of polymers from an engineering chemistry point of view. It does give me great pleasure to give you highlights of polymers during the course of this lecture because polymers have always had a special place whenever we talk about its role in chemistry and in engineering too. Because of late engineering plastics have assumed greater importance in a commercial and an industrial point of view. So those are some of the things which we will be going through over the course of this lecture. Study more in details about the different terminology we have in polymer chemistry and what properties of polymers make them actually so useful on a large scale production and day-to-day usage basis. So let's first start this lecture by giving you an idea of what the sequence will be of the topics covered in the course. Right, first up we'll have to familiarize ourselves with a few new terms in polymer chemistry. We'll be doing that in the first concept and then subsequently roll on to the types of polymerization processes, which are the addition and the condensation polymerism mechanisms. We'll see how one differs from the other markedly. Then we'll move on to an important branch of polymers, the plastics, and we'll take a look at how we use them so much in everyday life. We'll have a look at their properties, their advantages and their limitations as well. Then we'll conclude this video lecture with a look at some engineering plastics of real importance in our everyday life. We'll also have a look at the methods of preparation of these engineering plastics. So what exactly is a polymer? It is simply an assemblage of smaller molecules called monomers which are repeatedly linked together to form a macromolecule. And this big macromolecule is what we describe as a polymer. For example, take up an ethylene molecule, CH2 double bond CH2. This is what we call is a monomer. Now when N monomer molecules, that is N ethylene molecules, come together, they form what is known as polyethylene, abbreviated as PE, which is the polymer of our interest. Now, as you can see, this polyethylene has just one difference from the monomer structure. That is, the double bond shared between these two carbon atoms is taken off. It's only a single bond and you have a repetitive linkage being formed for polyethylene structure. There are a number of terms of interest when it comes to studying polymer chemistry, and let's first begin by defining what is known as degree of polymerization. Now, earlier when I illustrated the example of the formation of polyethylene, I said that N monomers, that is N ethylene molecules, come together to give us polyethylene. Now that N is what is known as the degree of polymerization. So it basically represents the number of monomer molecules coming together to form the polymer and is hence given by this formula: molecular weight of the polymer divided by the molecular weight of the monomer. So if someone comes up to you and says that the molecular weight of a PE polymer is 140, then you can easily comprehend that that polymer is made up of 5 ethylene molecules. Simply being the molecular weight given to you was 140, the molecular weight of ethylene is 28, which is nothing but 5. So the interpretation is 5 ethylene molecules came together, repeatedly linking with each other to give us the 140 molecular weight polyethylene polymer. Depending on the degree of polymerization and the molecular weight of the polymer, polymers are either classified as oligopolymers or high polymers. While polymers with a molecular weight of less than 5,000 fall under the first category, polymers with a molecular weight of greater than 10,000 come under the high polymers section. Now, the example we've seen so far of N ethylene molecules coming together to form a polyethylene polymer is an example of a homopolymer, which involves only one type of a monomer molecule, which was the ethylene molecule. What we're going to subsequently learn is going to be about heteropolymers, which involve 2 or more kinds of monomer molecules. Let's now go on to learn the types of polymerization. We'll first start with addition polymerization, which is also known as the chain growth polymerization. Now, the example you see on screen is where N-phenylethene molecules come together to form the polystyrene polymer. In this particular addition polymerization, you would have to note that there is no elimination of any molecule in the form of a byproduct, and the original monomeric molecule usually contains one or more double bonds, and the polymer formed is an exact multiple of the original monomeric molecule. Let's now move on to the next polymerization type, which is the condensation or stepwise polymerization. In the example shown on screen, hexamethylene diamine and adipic acid, two monomers, come together to give us a polyamide, which is the nylon 6,6 polymer. The two sixes there represent the 6 carbon atoms from hexamethylene diamine and the 6 carbon atoms from adipic acid, which come together to form the polymer. Now, in the condensation polymerization mechanism, there is always an elimination of small molecules in the form of byproducts, which is the main difference from the addition polymerization method. Now, in this particular example of nylon 6,6, we can see and realize that 2 water molecules are released as byproduct. Therefore, as you can see in the figure, the 2 hydrogen atoms bonded to nitrogen on either side of the hexamethylene diamine molecule combines with the 2 hydroxyl groups bonded to the 2 carbons on the either side of adipic acid, giving us 2 water molecules of condensation as a byproduct when the nylon 6,6 polymer is formed. Now, since we know that the condensation polymerization gives byproducts apart from the polymer, we are in a position to appreciate the fact that the formula we learned earlier for degree of polymerization will not hold true for the condensation polymerization mechanism, because now the molecular weight of the polymer obtained by condensation polymerization is no longer an integral multiple of the molecular weight of the monomer. So you just cannot have the ratios of the polymer molecular weight and the monomer molecular weight being taken and express it as a degree of polymerization, because you're losing some amount of mass in terms of byproducts in the condensation polymerization mechanism. Now, since we've encountered condensation polymerization, we'll be in a position to appreciate another classification of polymers known as the homochain polymers and the heterochain polymers. Under the homochain polymers, the polymer backbone or the main chain is going to be made up of only one species of atoms. For example, take a look at this example where I've taken a polyvinyl chloride, abbreviated as PVC. The polymer backbone or the main chain is made up of only carbon atoms. It's the same case when you take a polyethylene or PE as well. So if it's only one species of atoms making up the backbone, we call it a homochain polymer. Mostly it's made up of carbon atoms. Note that in PVC, chlorine is not in the backbone, but it's only a side chain. Now, when we jump to heterochain polymers, we have nylon 6,6 as the example, which is made up of obviously hexamethylene diamine and adipic acid. But you would have to note that the backbone is made up of both nitrogen and carbon atoms. So if you have a polymer backbone which is made up of different kinds of atoms, that is 2 or more species of atoms, we call that as heterochain polymers. Now, there's another important term we must know in polymer chemistry, and that is known as functionality. Functionality, simply put, is the number of reactive sites which tend to exist in a monomeric molecule. Now, to get it sorted, let me refer to a couple of examples in terms of monomeric molecules we already know. So, for instance, let's pick up hexamethylene diamine, which is one of the 2 monomers for the nylon 6,6 polymer production. Now, in hexamethylene diamine, the 2 NH2s, the 2 amine groups on either side of the CH2-6 group are 2 reactive sites, because it's those 2 NH2s which tend to get bonded with adipic acid to give us the nylon 6,6 polymer. So the functionality of 1,6 hexamethylene diamine is going to be 2. Now, if we move to glycerol, which is also a monomer, you have 3 hydroxyl groups, that is 3 OH groups, all of which are reactive sites. So the functionality of a glycerol molecule is going to be 3. Time now to move on to an important branch of polymers which we use in everyday life. Yes, the plastics. You can see from that image that we do use a lot of plastics in everyday life. So all the better that we get to know about them. Now, plastics are high molecular weight organic materials that can be molded into any desired shape by the application of heat and pressure in the presence of a catalyst. Well, man has now started developing plastics for all sorts of engineering applications, and plastics are being looked at as replacements for all kinds of things, from glasses, metal, ceramics to even wood. Now, it's because these plastics have some wonderful properties and advantages that man's affinity towards plastics has increased so much over the last few years. Now, when compared to a number of other materials, plastics are very light in weight and they also possess a low melting point. These can be advantages in many applications. Plastics also have a low coefficient of thermal expansion, and hence they tend to possess good thermal and electrical insulating properties. Now, in applications where metals tend to be highly prone to corrosion, plastics are corrosion resistant and they're chemically inert. So this property of plastics also tends to be a huge advantage at times. But just like a coin has the head and the tail, everything has a plus and a minus. And plastics do suffer from a few limitations such as deformation under load, embrittlement at low temperature, and also poor ductility. But I suppose all of us know that the biggest disadvantage of plastics is that they're non-biodegradable. Now, extensive research is being carried out all over the world to render plastics biodegradable because it's that only non-eco-friendly factor which is limiting the usage of plastics in everyday life. Now, plastics can be classified based on their usage into commodity plastics and engineering plastics. Under general commodity plastics, we have about 80 to 85% of plastics which have low to medium mechanical properties. These may include your PVCs, your polyethylenes, and such polymers or plastics which do not have a very appreciable mechanical properties. And moreover, these plastics tend to lose their properties, their characteristics at higher temperatures, and hence their usage is limited to the lower temperature range. And these are where engineering plastics differ. Now, they have excellent mechanical properties which do not degrade at even higher temperatures. Let's now take a look at a very important engineering plastic in polytetrafluoroethylene, that is PTFE, or more commonly known as Teflon. Now, you would have come across this polymer before because of its property of being non-sticky. The reason Teflon has a non-sticky character is because of the CF bond involved in PTFE. The CF bond is very strong because of the highly electronegative nature of fluorine, and it is extremely non-reactive, which gives it the characteristic of not being wetted by oil or water. And Teflon is generally obtained by the polymerization of water emulsion of tetrafluoroethylene, which is the monomer, in the presence of benzoyl peroxide under suitable pressure. Now, some of the other properties which may interest us in Teflon is the fact that it has an excellent thermal stability, and it also possesses extremely good electrical and mechanical properties. And it's these properties which translate in the final end uses of Teflon when it comes to the commercial aspect. Teflon is used for making gaskets, packings, pump parts, and even motors, cables, and electrical insulating materials associated with electrical fittings. Moving on to another very important engineering plastic, we have nylon 6. It is prepared from caprolactam by the ring opening mechanism. The 6 here represents the 6 carbon atoms from the caprolactam monomer. Now, nylon 6 does have a number of impressive properties such as possessing high tensile strength, elasticity, and also its tendency to be highly resistant to abrasion. And that's the reason it finds a number of applications in a broad range of products. Nylon 6 is used for molding purposes, for bearings, and also in toothbrushes. An important classification of plastics is done on the basis of structure. They're classified into thermoplastic resins and thermosetting resins. What we'll have a look at first are thermoplastic resins, and I've taken up the example of polyacrylonitrile, which is sketched on board. Now, the polyacrylonitrile polymer and all polymers which come under thermoplastic resins are generally formed by the addition polymerization method. And these generally tend to have long linear chains with very little amount of branching, as evident from the PAN network. And the PAN chains are generally detached from each other and are held together only by weak van der Waals forces of attraction. There's no form of covalent or ionic bonding which tends to exist between two PAN chains or two chains of polymers which come under the thermoplastic resin section. So it's just weak van der Waals forces of attraction due to the molecular weight which tends to exist between chains of the PAN network. Now, because it's only van der Waals forces of attraction here, when we tend to heat or cool a thermoplastic resin, the shape which it tends to attain is definitely remoldable, because it's only weak van der Waals forces that thermoplastic resins have the property of being remoldable. Now, the other branch of plastics when it comes to classification based on structure are the thermosetting resins. Now, thermosetting resins are formed by condensation polymerization, but the most important thing is that the polymer chains in thermosets or thermosetting resins are held together by strong covalent bonds. Remember, it was van der Waals forces of attraction in the case of thermoplastic resins, but in thermosetting resins, it's a case of strong covalent bonds. What that means is that thermosetting resins will consist of strongly built three-dimensional network structure, which tend to harden on heating, but this process is not reversible. That is, unlike thermoplastic resins, which are remoldable, thermosetting resins cannot be remolded because polymer chains are going to be held together by strong covalent forces. So they're going to be more strong and they're going to be more hard than the thermoplastic resin counterparts. And that's why that image of a bakelite telephone at the bottom of your screen. Bakelite is a phenol formaldehyde resin which has exceptional mechanical properties, and that's the reason it was used in the making of those ancient telephones. Right, with that, we're pretty much done on this lecture on the fundamentals of polymer chemistry. Let's just quickly revisit what we learned today. We started off by seeing what polymers are, macromolecules formed from the repetitive linkages of smaller molecules, which we call monomers. And then we started associating with the terminology used in polymer chemistry. We learned what is degree of polymerization, functionality, oligopolymers, high polymers, homochain polymers, how they differ from heterochain polymers, and we also took a sneak peek into the polymerization types, addition and condensation polymerization. We're now in a position to appreciate the fact that condensation polymerization mechanisms always have a byproduct associated with it apart from the regular polymer formed. Subsequently, we went on to distinguish thermoplastic and thermosetting plastics and also commodity and engineering plastics. I also gave you a couple of examples of engineering plastics, how they're produced, and the commercial applications of Teflon and Nylon 6. And what I would recommend is you also surf the net and find out a few applications of some engineering plastics we did not cover in this lecture, such as the polycarbonates and the polyurethanes. There are just so many in number, and it would really make for interesting reading the applications of those engineering plastics. Right, it's now time to evaluate yourself by answering those 4 questions on screen and just check how much you've learned from this video lecture. What I would recommend is you pause this lecture for the moment and go about answering those questions. And just in case you get stuck with a question or two, you can always roll back to the earlier part of this video lecture to find out the answers. Well, with that, it's time to draw the curtains on this course on the fundamentals of polymer chemistry. Hope all of you have got a lot from it, and more importantly are enthusiastic to learn about it more, because that's what we'll be unraveling in our advanced polymer chemistry section. Because you need not turn too far away from your study desk to see a polymer in a synthetic rubber itself, which we do use as an eraser. So we'll be learning more about the process of vulcanization of rubber and also about polymerization mechanisms in our advanced polymer chemistry lecture. So I'm looking forward to your company then. Till then, this is Manoj Ravi signing off. Goodbye.